Okay, so in this class we are going to deal with the numericals of chapter number 3, and the numerical statement says determination of the specific thrust and the specific fuel consumption for a simple turbojet engine having the following component performance at the design point at which the cruise speed and the altitude are. Mach number is 0.8 and the altitude is 10,000 meters. Compressor pressure ratio is 8. Turbine inlet temperature is 1200 Kelvin. The isentropic efficiency of the compressor turbine are 0.87, 0.90, of the intake is 0.93, and of the propelling nozzle is 0.95. Mechanical transmission efficiency is 0.99, combustion efficiency is 0.98, and the combustion pressure loss is 4% of the compressor delivery pressure. Okay. So this is the TS diagram shown here. So state A is going to represent the inlet state, and from state A to 01 this is the intake is more likely a diffuser, and from state 01 to 02 this is the compressor, and from 02, so this is the to 03 this is the combustion chamber. So delta PB, this is the pressure losses that are taking place in the combustion chamber, and P03 by P04 is the from state 03 to state 04 this is the expansion, and from state 04 to 05 this is the expansion in the nozzle side. Okay, so the nozzle is going to expand the flow up to a pressure P5 which is equal to P ambient. Okay, and CA square by 2 CP is going to represent the dynamic component. Similarly, C5 square by 2 CP is going to represent the dynamic component. Okay. So this is the temperature raise from state 01 to 02 in the compressor, and this is the temperature drop delta T in the turbine. Okay, so we are required to find out the specific thrust and the specific fuel consumption for this turbojet engine. Okay, so first of all, from the ISA table at this elevation of 10,000 meters, we can find out the value of the ambient pressure and the ambient temperature. So this will come out to be 0.2650 bar, and the ambient temperature is 223.3 Kelvin. Since you know the value of TA, so we know this is air, so you can find out the value of the speed of sound at this temperature, which is under root gamma RT. So this will come out to be 299.5 meter per second. So CA square by 2 CP is CA is the velocity of the air that is entering into the aircraft, which will be equal to the Mach number times the acoustic speed. Mach number is 0.8 and the acoustic speed is 299.5. So CP is 1.005, and this is multiplied with the 1000 because CP is expressed in terms of joule per kg into Kelvin. So CA square by 2 CP, with this will come out to be 28.6 Kelvin, and T01 is equal to TA plus CA square by 2 CP. Okay, because the stagnation states T1 and TA are same, so we can say T01 is equal to TA plus CA square by 2 CP. So TA is 223.3 and CA squared by 2 CP is 28.6. So T01 will become equal to 252 Kelvin. You know, and we can find out the value of the pressure ratio for the intake, which is P01 by PA. So this is equal to 1 plus intake efficiency CA square by 2 CPTA rest to power gamma or gamma minus 1. Okay, so intake efficiency is 0.93 and CA square by 2 CP is 28.6 and TA is 223.3, the rest of power 3.5. So P01 by PA is 1.482. So P01 will be equal to 1.482 times PA. PA is 0.2650. Okay. So P01 will come out to be 0.393 bars. And at the outlet from the compressor, P02 is equal to P02 by P01 times P01. So this is the pressure ratio which is given 8, and P01 is already known, which is 0.393 bar. So P02 will become equal to 3.144 bars. T02 minus T01. We already know T02 minus T01 is equal to T01 divided by compressor efficiency into pressure ratio raised to power gamma minus 1 by gamma minus 1. So T01 is 252 and the compressor efficiency is 0.87 and pressure ratio is 8 raised to power gamma minus 1 by gamma is 1.1 divided by 3.5 minus 1. So T02 minus T01 is 235 Kelvin. Okay. So T02 will be equal to 234.9 plus T01. T01 is 252 Kelvin. So T02 will come out to be 486.8 Kelvin. Okay. Now we know that the turbine work produced is equal to the compressor divided by the mechanical efficiency. So whatever the amount of the work produced by the turbine is going to drive the compressor. Okay. So T03 minus T04 times CPG times mechanical efficiency is the net work produced by the turbine, and this is equivalent to the power required by the compressor, which is CP8 times T02 minus T01. So CPG is 1.148, CPA is 1.005, T02 minus T01 is 235, and mechanical efficiency is 0.99. So the drop of the stagnation temperature in the turbine is roughly around 207.7 Kelvin. Since we know the value of T03, which is maximum cycle temperature, is 1200 Kelvin, and T04 will be equal to T03 minus 207. So T04 will come out to be 992.3 Kelvin. Similarly, you can find out the value of P03, which will become equal to P02 into 1 minus del PB by P02. This is the pressure loss in the combustion chamber divided by the P02, which is 4% of the pressure drop of the compressor delivery pressure. So P03 will come out to be 3.018 bar. We know the turbine efficiency is the ratio of the actual work produced divided by the isentropic work produced. So the actual work produced is T03 minus T04 and the isentropic work produced is T03 minus T04 dash. Okay. So the quantity of the work produced is equivalent to the drop of the enthalpy, and this enthalpy is taken and written in terms of the temperature difference instead of being written in terms of the enthalpy. So we have written in terms of the temperature difference. Of course, Cp and Cp are cancelled out. So from there you can find out the value of T04 dash, which will become equal to T03 into 1 minus 1 hour turbine efficiency into T03 minus T04. So T03 minus T04 is 207 and T03 is the maximum cycle temperature, which is 1200 Kelvin, and turbine efficiency is 0.90. So T04 dash will become equal to 969.2 Kelvin. So from there you can find out the value of the P04. P04 is equal to P04 by P03 is equal to T04 dash by T03 raised to power gamma or gamma minus 1. Okay. So T04 dash by T03. T04 dash is 969 and T03 is 1200 Kelvin raised to power gamma or gamma minus 1, which is 4, and P03 is 3.018 bar. So you can find out the value of P04, which is, so you can find out the value of P04, which is 1.284 bars. The nozzle pressure ratio is therefore the expansion in the nozzle is from state 4 to 5. So PA is equal to P5. The expansion is done up to the atmospheric pressure. So P04 by P05 or P04 by PA, you can write it, which comes out to be 1.284 divided by 0.265. So this is 4.845. Okay. So in order to find whether the nozzle is to be choked or not, so you can compare it with the critical pressure ratio, and the expression for the critical pressure ratio is given as P04 by Pc is equal to 1 over 1 minus 1 over nozzle efficiency into gamma minus 1 divided by gamma plus 1 bracket close raised to power gamma divided by gamma minus 1. Okay, so 1 divided by 1 minus 1 over nozzle efficiency is 0.95 and gamma minus 1 is 0.33, gamma plus 1 is 2.33 raised to power gamma or gamma minus 1 is 4. So P04 by Pc is 1.914. So you can compare these two pressure ratios and you can find out that the nozzle is choked because Pc is actually greater than Pa. Critical pressure is greater than Pa. Of course, the nozzle is said to be choked. So if the nozzle is to be choked, then T5 will be equal to Tc and P5 will be equal to Pc. So T5 will be equal to Tc, so which is equal to 2 by gamma plus 1 times T04. Okay. So T04 is 992.3 and gamma plus 1 is 2.33. This is multiplied by 2. So T5 will come out to be 850.7 Kelvin. Similarly, P5 is equal to Pc. P5 is equal to Pc is equal to P4 times 1 over P4 by Pc. Okay. So P4 by Pc is already known, which is 1.914, and P04 is 1.284. So P5 will come out to be 0.671 bar. Similarly, you can find out the value of rho 5, which is rho 5 is equal to rho c. Rho c is equal to Pc by Rtc. R is 0.287, Pc is 0.671. So we have converted the bar into kilopascal, which is multiplied by then 100, and Tc is 850.7 Kelvin. So rho 5 is 0.275 kilogram per meter cube. And for the speed of the sound, which is coming at the state 5, is equal to under root gamma Tc. Okay. So since the nozzle is to be choked, so you can find out the speed of the jet coming out from the nozzle is at the speed of sound, okay, which is equal to under root gamma Tc. Gamma is 1.33 and R is 0.287. Tc is 850.7 multiplied by 1000. This speed of sound will come out to be 570.5 meter per second. Okay, and we can write the expression A5, area at the exit divided by the mass flow rate, can be written in terms of 1 over rho 5 times C5. So rho 5 and C5 are already known. You can find out the value of the area per unit mass flow rate, which is 0.006374 meter square into second per kg. Okay. And the specific thrust is C5 minus Ca plus A5 by m times Pc minus Pa. So we have this expression A5 by mass flow rate, and this is the thrust because of the pressure force, and this is the thrust because of the momentum. So together this will give you the specific thrust of roughly around 9590 Newton into second per kg. Okay. So again, in order to find out the specific fuel consumption, you need to find out the value of the fuel air ratio. So in order to find out the value of the fuel air ratio, you need to look at the value of the theoretical fuel air ratio divided by the combustion efficiency. Combustion efficiency is 0.98 and the theoretical fuel air ratio is 0.0194. Of course, you can find out from the same graph which we have done for the chapter number 2 numericals, and from there you need to find out the combustion temperature raise. How much is the amount of the raise in the combustion chamber temperature has taken into account. So this is equal to 713.2 Kelvin. Okay. So from this figure, you can find out the value of the theoretical fuel air ratio, which comes out to be 0.0194. and from there you can find out the value of the actual fuel air ratio, which is theoretical fuel air ratio divided by the combustion efficiency. So the actual fuel air ratio is 0.0198, and the specific fuel consumption will become equal to actual fuel air ratio divided by the specific thrust. Okay, and multiplied by 3600. So this will give you in terms of hour, not the second. So specific fuel consumption will become equal to 0.121 kg per hour into Newton. Now we have the next problem statement, and the problem statement says the following data applies to a twin spool turbofan engine with a fan driven by the LP turbine and the compressor driven by the HP turbine. Separate cold and hot nozzles are used. Overall pressure ratio is 25. Fan pressure ratio is 1.65. Bypass ratio is MC by MH. Bypass ratio is the ratio of the mass flow rate of the cold air divided by the mass flow rate of the hot air, which is given as 5. And the turbine inlet temperature is 1550 Kelvin. Fan, compressor, turbine polytropic efficiencies are 0.90. Isentropic efficiency of each propelling nozzle is 0.95. Mechanical efficiency of each spool is 0.99. Combustion pressure loss is 1.50 bar, and the total air mass flow is 215 kg per second. So we are required to find out the value of the thrust and the specific fuel consumption under the sea level static condition, where the ambient pressure and the temperature are 1 bar and 288 Kelvin. Okay. So remember, this is a turbofan engine where the fan is driven by the high pressure turbine. So remember, this is the turbofan engine where the fan is driven by the low pressure turbine and the compressor is driven by the high pressure turbine. So the high pressure turbine is going to drive the compressor and the low pressure turbine is going to drive the fan. And the rest of the expansion is done in the nozzle in order to produce the necessary amount of the thrust. So as far as isentropic and the polytropic efficiencies are concerned, we know that the n minus 1 by n expression for the compression and the expansion can be written for the compressor and the turbine as n minus 1 by n is equal to 1 over polytropic efficiency of the compressor into gamma minus 1 by gamma for the air side, because when we are going to deal with the compression process, air is going to enter into the compressor, and after the compression air is coming out from the compressor. So we are going to use polytropic efficiency of the compressor is given as 0.9, and gamma minus 1 by gamma is 1 over 3.5. So gamma is 1.33. So for the compression, n minus 1 by n comes out to be 0.3175, and for the expansion, n minus 1 by n is equal to polytropic efficiency of the turbine times gamma minus 1 by gamma for the gas side. And for the gas side, gamma minus 1 by gamma is 1 by 4, and the polytropic efficiency of the turbine is 0.9. So for the expansion, n minus 1 by n is equal to 0.225. So under these static conditions, T01 is equal to TA. Static conditions, it means the dynamic component is absent. CA square by 2CP is absent. Therefore, T01 is equal to TA and P01 is equal to PA. So using that, we can relate the temperature and the pressure in terms of the n minus 1 by n index. So T02 by T01 is equal to P02 by P01 rest power gamma minus 1 by gamma. Okay, so T02 is equal to 1.65, which is pressure ratio, times gamma n minus 1 by n for the compression is 0.3175 multiplied by T01, which is 288 Kelvin. So T02 will come out to be 337.6 Kelvin. So T02 minus T01 is equal to 337.6 minus 288. Okay, so TA is T01, which is 288 Kelvin. So you can find out this difference, T02 minus T01, which is 49.6 Kelvin. Okay, and P03 by P02, P03 is 25 and P02 is 1.65, which is pressure ratio. So P03 by P02 is 15.15. And for the T03 is equal to T02 times P03 by P02 raised to power gamma minus 1 by gamma. Okay. So this is expression for the isentropic compression. Since we are going to deal with the polytropic compression, so therefore instead of using gamma minus 1 by gamma, we have used here as n minus 1 by n. Okay, so T02 is 337.6 and the pressure ratio is 15.15 raised to power 0.3175. So T03 comes out to be 800 Kelvin and T03 minus T02 will become equal to 462.5 Kelvin. The cold nozzle as the fan pressure ratio is 1.65 and the critical pressure ratio for this nozzle is calculated which comes out to be 1.965. Okay, so it shows that the cold nozzle is not choking because PC is actually lower than PA and thus the cold nozzle thrust is given by simple the momentum thrust. Okay, mass flow rate at the cold side times the velocity of the uh, hot velocity of the air at the cold side. Okay, the nozzle temperature drop can be calculated as T02 minus T8, which is equal to the nozzle efficiency times T02 into 1 minus 1 over P02 by PA raised to power gamma minus 1 by gamma. So the nozzle efficiency is 0.95, P02 is 337.6 and P02 by PA is 1.65 raised to power 1 over 3.5. So T02 minus T08 is 42.8 Kelvin. And for the C8, which is equal to under root 2 Cp, T02 minus T08. So you can find out the value of Cp. So you can find out the value of C8 is 2 into 1.005 into T02 minus T08 is 42.8 into 1000 into under root of 1 over 2. So C8 is equal to 293.2 meter per second. Since the bypass ratio B is 5, so you can find out the value of the mass flow rate at the cold side, which is MB divided by B plus 1, where B is the bypass ratio. So this M is equal to 215 times 5 divided by 6. Okay. So mass flow rate at the cold side is 179.2 kg per second. So the fan thrust at the cold side is 179.2 times 293.2. Okay. C8 is 293.2. So the thrust at the cold side is roughly around 52.5 kilonewton. Now for the HP rotor, we can start the calculations which we have performed in the previous numericals. T04 minus T05 is CPA by mechanical efficiency times CPG into T03 minus T02. So T03 minus T02 is 462.5, CPA is 1.005 and CPG is 1.148 and the mechanical efficiency is 0.99. So T04 minus T05 is 409 Kelvin. And for the LP loader and for the low pressure turbine, T05 minus T06 is equal to bypass ratio plus 1 times CPA divided by the mechanical efficiency times CPG into T02 minus T01. Okay, so you can find out the value of the temperature drop from 5 to 6, which is 263.2 Kelvin. And hence finally you can find out the value of T05 and T06. T05 will come out to be 1141 and T06 will come out to be 877.8. Now P06, for the calculation of the P06, if you recall P04 by P05, which is T04 dash by T05 dash raised to power n over n minus 1. So T04 and T05 are given. So you can find out the value of P04 by P05, which is 3.902. And P05 by P06 is T05 by T06 raised to power n over n minus 1. So this is 3.208. And since P04 is equal to P03 minus the pressure losses, so this is 25 into 1 minus 1.50. So P04 is 23.5 bar, and P06 is finally P04. We can rearrange the equation and we can write the expression of P06 as P04 divided by P04 by P05 times P05 by P06, such that these are cancelled out. So we know the value of these ratios, which is P05 is 3.902 and P05 by P06, which is 3.208, and P04 is 23.5. So finally you will get the value of P06 as 1.878 bars. And the hot nozzle pressure ratio is P06 by PA, which is 1.787. While the critical pressure ratio, so you need to compare this because we need to find whether the nozzle is to be choked or unchoked. So we know the expression of the critical pressure ratio, which is 1 over 1 minus 1 over nozzle efficiency times gamma minus 1 divided by gamma plus 1 raised to power gamma minus 1 by gamma. So P06 by PC is 1.914, and this nozzle is unchoked because PC is actually less than PA. Okay. Hence P7 is equal to PA. Okay. So T06 minus T07 will be computed as the nozzle efficiency times T06 into 1 minus 1 over P06 by PA. PA or P7, these are equal raised to power gamma minus 1 by gamma. You can find out the value of the temperature drop from 6 to 7, which is 122 Kelvin. Okay. Similarly, you can find out the velocity of the jet coming out from the exit at C7, which is 528.3 meter per second. The mass flow rate at the hot site is m divided by b plus 1, bypass ratio plus 1. mh is equal to 35.83 kg per second. And specific fuel consumption is this mass flow rate times the velocity at C7, which is 18.931 kilonewton. Okay. So the total thrust is the thrust at the hot side and the thrust at the cold side. So total thrust will come out to be 71.5 kilonewton. And of course, for the specific fuel consumption, there has to be the proper uh, way to write the specific fuel consumption. A specific fuel consumption is written in terms of the mass flow rate divided by the total thrust. So this will come out to be 0.0403 kilogram per hour into Newton. So this mass flow rate is written in terms of the kilogram per hour, and this is 35.83 multiplied by 3600 times this is the fuel air ratio, which is 0.0223. So this is the mass flow rate in terms of the kg per hour.